All right, so in this video, we're going to continue investigating electric potential. And here we're going to look at electric potential and potential energy due to point charges. So we can maybe start with let's say a single point charge, then maybe like a multiple point charges, some finite number of point charges, and move to a little more complicated continuous distribution of charges. So for example, here we start with charge Q. That means when I say single charge, I mean single source charge. So let's say we have a single source charge here, and this charge Q is basically sitting there. And remember, because of its charge, right, it affects all this space around it. And then what we can do here is we can assume that all that region is filled with potential, right, which is its scalar effect. Now, one thing I can do here is if I look at some distance, r from this charge, I can see that those, you know, those points are exactly the same distance from the charge. So the potential at those points exactly the same. So that's why those are known as equipotential surfaces. Equipotential surface means that because that's in a way you can think of like as a three-dimensional, right? It's like a sphere surrounding that charge Q. Then you can say that the potential is exactly the same everywhere on that surface. So that's why they are called equipotential surfaces. Same thing is here. Those are also equipotential, you know, it's also an equipotential surface. It's one surface where the potential is exactly the same. That means all this region is filled then with potentials like that. Now, if I look at then some point A, then I can think of like, let's say, all right, so there's a potential that I can calculate at point A because that point A has a finite distance RA from the source charge. And then I can look at in terms of some point B. And that means, and the point B is also finite distance from the source charge, then there's also a potential over there. Okay. Now, as I already talked about before, we can relate that change in potential between point B and A, right, VB minus VA, to the also the electric field, right, that is present in that region. Now, the idea here is that I can relate then change in potential to the negative of the integral of E dot ds. Okay, so I already showed you this, gave you some example, but sort of like, let's say this is basically the main equation that we have in this part. That means, using this equation, VB minus VA, we have the negative of integral going from point A to point B, E dot ds. Because as soon as I bring a test charge at that point A, and then let's say we move that test charge from point A to point B, then I can use the left side of the equation, delta V, to calculate then technically the change in potential energy, right, by multiplying Q naught to that. So Q naught times delta V, I can calculate the change in potential energy for that test charge going from A to B. Equivalently, I can calculate the change in potential energy, right, delta U, by calculating Q naught times this integral, negative E dot ds. I can also, do that. There are two ways then I can use that information to calculate, let's say, electric potential energy. I can also use this left side of the equation technically then to calculate the force, right? Because I know that as soon as you bring a test charge, there's a force acting on it because there's a field already over there. All right, so at point A or at point B, I can individually calculate the electric field, which is K, Q, or R square, or I can generalize it for any point, during this, the path from A to B. Well, there's going to be electric field, right? That means all those regions are filled with electric field. So then E dot ds is K, Q, or R square, R hat dot ds. Technically, remember, so when you're doing that product is between two vectors. So because electric field, this is the magnitude, and then this is the direction. So you're technically doing the dot product between those two. Okay, so R hat vector and then ds vector. Okay, and because there's an angle theta between them, so then there's also like ds cosine theta. So this becomes, r ds, like, r hat d, dot ds, right? So where then this ds basically becomes ds cosine theta. Then r hat, if you're doing in terms of magnitude, right? So let's say if you have, sorry, so r hat dot ds, those are two vectors. And remember, dot product between any two vectors, a dot b is magnitude of the first one times magnitude of the second one, then times cosine of angle between them. Well, magnitude of the r hat is just 1. So it's 1 times then ds then times cosine of theta. That means this entire thing just becomes ds cosine of theta because magnitude of r hat is just 1. All right. So that's why one of the things we can do here is, which I already showed you, right? So if we take then and replace, let's say in this equation, right, this E dot ds. So the idea here is that I can replace it with then basically k q over r square, dr, and then move the kq out of the integral. So that becomes just basically integral of 1 over r squared dr, which gives you, negative 1 over r. It cancels that negative over there, so it becomes kq over r. And then this is then the change in potential energy, which basically shows that VB minus VA is just basically K Q over RB minus K Q over RA, which means that this is potential at point B minus potential at point A. And the electric force is a conservative, and then the field is a conservative field. All right. So now, this equation, V equals KQ over R, it is generally used for potential due to some kind of source charge. That means you can use that for find the potential, this distance R from the source charge, and find the scalar effect of that source charge. Okay. Obviously, whenever we're considering, some kind of scalar quantity, like, distance or even like or time, potential, right? Those things always, easier to represent if there is a reference. Let's say, how much distance did you cover? Well, what is the reference? Well, whenever, like, let's say when time was 0 or something like that, right? Or your house was the reference. So in this case, what we do, we take always the reference as the infinity. And we say that, okay, so when you're doing VB minus VA, for example, take RA to be infinitely far away, so then this basically is 0. That means your delta V here is just basically whatever you calculated VB. So that's why if you have a source charge, then if you're considering some point P, you can say, all right, so this point P has a distance RB from the charge, then point A is then has a distance infinity from the charge. So then delta V is technically just potential at point B. So that's why what we can do here is we can just calculate the potential at distance R from the charge, and we can say that this is the potential relative to the, reference position, which is infinity. But what if we have another charge over here? So another source charge. So let's say this is source charge 1, this is source charge 2. Well, in that case, that point P will be affected by both of those, R2. That means at that point, now I can look at in terms of potential 1 plus potential 2. And there is no direction, there is no vector, there is no components and things like that for the potential. Potential is just a number with the unit. So this becomes basically KQ1 over R1 plus KQ2 over R2, which is basically sum of those potentials. What if you have a third one and the fourth one? Well, no big deal, right? So just basically the direct, distance, right? R4, R3, all you need is how far away it is and what is the charge of Q1, Q2, Q3, Q4, right? And then just add them together. And it's an algebraic sum. This one is always an algebraic sum. What if this guy is negative? Well, then this will be negative. And you can just basically add or subtract just algebraically and get the net potential. Okay. So that's why this equation represents for a group of point charges. Okay. And it's always, relatively straightforward to calculate the potential because you're dealing with a scalar quantity. All you need is the charge and the distance to that point. So let's look at this example here. A point particle has a charge equal to 2 microcoulomb and is fixed at the origin. What is the electric potential V at the point 4 meter from the origin, assuming that V equals at infinity? Okay. So what I do here is I choose my source charge here, and it's positive. So let's say I put like plus Q, and I want to put this at the origin. All right, so let's say at the origin, we're told it's at the origin. Then it says find the potential 4 meter from the origin. All right, 4 meter from the origin, but where? Left, right, up, down? Well, doesn't really matter. As long as it's 4 meter from the origin, we're all going to get the same, potential. So let's make it simple. Let's say here's that point P. 4 meters in this direction. So let's say this is, R, which is equals to 4 meters. Then I can calculate the potential for part A, which is KQ over, R. And this is then 9 times 10 to the 9, then times 2 times 10 to the negative 6 coulomb divided by the 4 meters. So calculate basically the potential at that point P due to this a source charge. All right, so if I calculate, I'm going to get 4,490 volts. Okay, so I can then say potential is equals to 4.49 kilovolts. Kilo is basically 1,000. So this is then the answer for that part A. Part B says, how much work must be done to bring a second point particle that has a charge of 3 microcoulomb from infinity to a distance of 4 meters from that plus 4 microcoulomb charge. Sorry, plus 2 microcoulomb charge. Well, that means what we're doing here is this. We want to know how much work must be done. And remember, we have to do work, right, on another test charge that is also positive, because field is going to be pushing it away from this source charge. That means in order for it to come close to this point P for to basically positive charge, test charge to another positive source charge, we have to do work. We have to actually push it. That's why work done by us is positive. And what it will do, it will then increase potential energy. So then delta U is equal to Q times then delta V. And technically we do have delta V because one other point is, when it says from infinity, that means we can say that the other point is just infinity. So delta V is just, let's call this, I guess, point B, right? Point A is infinity, delta V is just potential at point B. All right, so then Q is, so Q is plus 3 times 10 to the negative 6 coulomb. Then delta V is 4,490 volts. So then the work done here is end up being 13.5 millijoules. Okay, so that's the work done for this 3 microcoulomb charge to come from infinity to this point B. All right. Now it says, consider the potential energy of a system of 2 charged particles. If V2 is the electric potential at point P due to a charge Q2, the work on the external agent must do to bring a second charge Q1 from infinity to P without acceleration, which means that without changing the kinetic energy, right, is Q1 times V2. Okay, this work represents a transfer of energy into the system. It's just like when you take an object from ground and you move it up. You move it up such that it's basically moving at, it's not accelerating, right? You're just basically moving at constant speed, but you are moving it up. So you are, transferring energy as a potential energy. And that's what we have, right? Taking an object and moving upward at constant rate, we are transferring energy. That's why it gains potential energy. How the object gains potential energy when you're moving it up? Well, we are doing work on it, right? We're pushing up and we're transferring energy. But when we let go, then the gravity does work, and gravity conserves energy. But when, some kind of external agent, push, pull, right, acting on the system, they actually do indeed change the energy of the system. All right. And that's what we have. So think like this. So you have 2 charges, Q1 and Q2. You bring the other one to, basically you bring them close to one another, distance this R12, then you can calculate potential energy for this system. So U is the potential energy to bring the other one to at this point is K, Q1, Q2, or R12. All right. So again, something that we already talked about. Okay. So this is basically the potential energy of the system of these 2 particles. What happens if you bring another one? Well, we talked about, right? Then you look at, in terms of if this is Q3, so this becomes R13. So then you have another one, right? U on 13. So it becomes KQ1, Q3 over R13. And then you also, this one, 3 interacts with 2. There's also U23, KQ2, Q3, R23, right? And then add them all together, assuming that this was 1, 2, adding them together to get the total energy of the system. Okay, so that's one thing we can do. All right, so if the charges are at the same sign, then U is positive, right? Because remember, we are not using absolute value for the calculation of this potential energy. Q1, Q2, both positive, U is positive. So the positive work must be done by an external agent on the system to bring the two charges near each other. Again, because positive, positive, they're always going to repel each other. To bring them close, you have to do work. External agent has to do work, because as soon the forces between them pushing them apart. So the field does negative work in that case. That means in order for us to bring them close, we have to do work. External agent has to do work, and that's why the potential energy increases. Okay. Same is true for negative, negative. Same is true for negative, negative. That means positive, positive, or negative, negative. That means same sign. You have that. If the charges are of opposite sign, that means think like this: you move it from infinity just a little bit, and you let go. It will already be attracted. The field will already pull it toward the other charge. You don't have to do anything. So that means the field is going to do a positive work, just basically just on its own it will move toward the other charge. But then when the field is doing positive work, potential energy decreases. And that's what we have. It means negative work is done by external agent against the attractive force between the charges of opposite sign as they are brought near each other. That means in order for you to bring the charge to the, those two charges of opposite sign. So let's say you have a negative sitting there. To bring a positive close to the negative without speeding up, we have to, apply force, right? This has to be our hand, slowing it down such that it's moving toward the negative charge, but without speeding up. Because as soon as we let go, it's going to start speeding up because the attractive force between them. So that's what we have in terms of, this type of scenarios. Okay. Okay, so then you can say, right, so let's remove the charge Q1, and it just says that, let's say at some point P, you can calculate the potential. That means if you have a source charge, any point P, you can calculate the potential. So if there are more than two charges, then find U for each pair of charges, then add them together. As I mentioned, right, add them algebraically. That means U12 plus U13 plus U23. You bring a fourth one, then becomes U14 plus 4 interacts with 2 plus 4 interacts with 3, right? And then just add them together. You can say, right, dot, dot, dot. So this is then the net potential energy. Okay. So total potential energy of a system of point charges equal to the work required to bring the charges one at a time from infinity and separate, to their final position. So let's look at then this example here. You have a point charge Q1 plus 2 microcoulomb is held stationary at the origin. Second point charge Q2, which is negative 4.3 microcoulomb, then we're going to move that from position A to position B. Then we're given position A to have a coordinates of x equals 0.15 meter, y equals 0, to the position of x equals 2.5 and y equals 2.5. So basically moving it from point A to point B. How much work is done by the electric force? Again, work done is equals to the integral of force dot dl. Okay. Well, we don't want to use this equation. This is going to be a terrible equation for us to use. Let's say if you try to, find the force at every second, at every meters and things like that. One thing we know already that this force allows us, because it's a conservative, it tells us that work done is equals to then negative delta U. Okay. Which means it equals to the negative potential energy at point B minus potential energy at point A, or we can say work done incorporating the negative becomes potential at A minus potential at B. That means the easiest way to find the work done by the electric force on Q2 is to find, when they're interacting, right? What is the potential energy of the system at point A? What is the potential energy of the system at point B? Then find their difference, and that's the work done. Very easy. So let's look at that. So when they are at position A, so let's say position A, then I can write RA is equals to 0.25 meters. Then potential energy at A is equals to K Q1 Q2 divided by RA. Okay, so let's calculate that. Potential energy at A equals 9 times 10 to the 9. Then 2.4 times 10 to the negative 6 coulomb. Then minus 4.3 times 10 to the negative 6 coulomb. Then divided by 0.25, sorry, 0.15. I got it wrong here. So 1.5 meter, then we're not squaring. That's so 0.15 meter. That means I calculate and I make sure that I'm not using any absolute value. So there's a negative there. That means my potential will be negative. So negative 0.6184 joules. That's my potential at point A. My potential at point B is equals to then 9 times 10 to the 9, then times again 2.4 times 10 to the negative 6, negative 4.3 times 10 to the negative 6 coulomb, divided by, well, this will be then RB. How do we find RB? Well, I'm given this distance and that distance, so RB is equal to then square root of, right, 0.25 square plus 0.25 square. That's my, distance. I calculate this. RB is equals to 0.3536 meters. Then 0.3536 meters goes here, and I calculate, and I'm going to get negative 0.2623 joules. That's my potential energy at point B for that system. All right, so then work done is the difference between them. So work done is equals to potential at A, potential energy at A, so negative 0.6184 joules, minus potential at B, which is negative 0.2623 joules. Okay. Again, you can see, right, both of those potential energies are negative because one of the charges are negative, potential will be negative. But the question is this: will the potential energy increase or decrease? You can look at it from here directly, comparing potential at A, potential at B. Which one is a larger number? Which potential energy is higher? Well, remember, this is something we're dealing, in this case, we're dealing with a scalar quantity. So this is a smaller number than that because this is less negative than the other one. That means technically our potential energy increased as we went from point A to point B. Now we can also see from that delta U, when delta U increases, that means work done here is always going to be negative. So let's calculate the work done. If the work done is negative, that means potential energy did indeed increased. Well, if I calculate this, I'm going to get negative 0.356 joules. And that agrees. See, my work done is negative. That means my potential energy indeed increased, going from negative 0.6 to negative 0.2, which is technically a larger number. All right, so here's another example. 3-point charges are on the x-axis. Q1 is at the origin, Q2 is at the x equals plus 3 meters, and Q3 is x equals plus 6 meters. Find the electrostatic potential energy of the system of charges for the following charge values. Q1, Q2, and Q3, they're all the same, plus 2 microcoulomb. And for part B, Q1 and Q2 are plus 2 microcoulomb, Q3 is negative 2 microcoulomb. Assume the potential energy is 0 when the charges are very far from each other. Now, how do we do this? Well, think like this. First, let's assume those are not there. You bring Q1 and put it there. There's nothing there, so it makes no effort to bring the Q1. Then we bring Q2 over here. Then I can say, all right, so my potential 1, 2, K, Q1, Q2 divided by the, let's call this, R12. Okay, divide R12. And then I bring the Q3. Then I have U13, which is K, Q1, Q3 over R13, which is this one. And then there's also U23, which is K, Q1, Q3. So Q2, Q3 over R23, which is then this distance. Well, what we do then, we add them all together, right? We add them all together, and because they're all positive, right? So it becomes basically K times, they all have the K, I can factor out, becomes Q1, Q2 over R12 plus Q1, Q3 over R13 plus Q2, Q3 over R23. Okay. All right, so one thing we have here is this, right? So R12 is 3 meters, R13 is 6 meters, and R23 is also 3 meters. And those are the values for the charges. If I plug in all of those values, right, into this equation, I'm going to get 30 millijoules. Okay, Pretty straightforward, right? So take those distances, plug in, those charges, plug in, and that's what you get. That's part A. Part B says, it says that take just Q3 to be negative. Well, but here's the thing. If I make the Q3 negative, so if I'm calculating this one, right? See, then Q3, so this becomes plus Q1 plus Q2 over R2, 1, 2, then plus Q1, but then minus Q3, right? It's what I mean is just this is a negative number, R1, 3, then plus Q1, then negative Q3, which means that in a way, think like this. If I do this, we're going to be like that. So this is going to be the negative, and this is going to be the negative if I do that. Or, you know, this is 2, 3, 2, 3. That means now I'm going to pretty much do a subtraction. And if I plug in all the values again, I'm going to get negative 5.99 millijoules. You can see, right, just having one of them negative makes the whole thing completely different. You now have 1 and 2 negative potentials. So you're not adding them, you're actually, subtracting. All right, so remember again, be careful with that. All right, so here's one more example. As shown in the figure, a charge Q1 equals 2 microcoulomb is located at the origin, and a charge Q2 equals negative 6 microcoulomb is located at x equals 0, y equals 3 meters. Find the total electric potential due to these charges at point P. And then here's point P, whose coordinates are x equals 4, y equals 0. All right, so let's do that first. So A is this. Well, it's a potential. That means I can say that at that point P, there is a potential due to 1 and potential due to 2. And I can add them together to get the total potential. D1 is K Q1 over R1. D2 is K Q2 over R2. So I can factor out K, becomes Q1 over R1 plus Q2 over R2. Then I say, all right, so the net potential is equals to 9 times 10 to the 9. Then Q1 is 2 times 10 to the negative 6 coulomb over the distance of 4 meters. R1 is 4 meters. Then plus negative 6 times 10 to the negative 6 coulomb divided by R2. Well, what is R2? Well, this is R2. So R2 is equal to then square root of 3 squared plus 4 squared. So basically 5 meters. Right? So simple enough. So we can get it as 5 meters. Okay. And then calculate net potential energy. Net potential, which will give us negative 6.29 kilovolts, like this. That means 6.29 kilovolts or 6.29 times 10 to the 3 volts. All right, so that's part A. Part B, it says, you can see, right, how easy it is. Just, comparing to the net electric field. Net electric field, I had to break it down into components. This is, this is actually would have been in that direction and so on and so forth, right? But, in terms of then potential, just find the value, just add them algebraically. Part B, it says, find the change in potential energy of the system of 2 charges plus a third charge Q3, which is 3 microcoulomb, as the latter charge moves from infinity to that point P. Because here's the thing, you can calculate the potential at some point P, but when you're calculating potential energy, well, you need to have a charge, some kind of test charge, right, in order to calculate potential energy. All right, so that means what we're saying is that imagine you bring then some kind of positive 3 microcoulomb test charge and place it over here. So let's say Q3. So then find the change in potential energy. That means what we can say is that this potential at point P is the combination of delta V, which is potential at point P minus potential at infinity. So this is basically potential at point P because potential at infinity equals 0, referencing infinity. That means then I can say then delta U is equal to Q3 times delta V that I already have here. See, I can bring that Q3 there and calculate in terms of U12, U13, and something like that, right? But I don't need to because I have this equation, change in potential energy equals Q3 times change in potential already at that point P. So then delta U is equals to, well, my Q3 is 3 times 10 to the negative 6 coulomb, and my delta V was negative 6.29 times 10 to the 3 volts. Okay. Put them together, I get negative 1.89 times 10 to the negative 2 joules. And that's my change in potential. Change in potential energy. Okay. All right. And the last part says, you are working through the example with the classmate, and she says, wait a minute, in part B, we ignored the potential energy associated with the pair of charges Q1 and Q2. How would you respond? Well, again, the idea here is this, right? So in the previous, example, we started from the scratch. There was nothing there, so we brought first one, and then the second one, and then the third one, so that we have to individually calculate. But here we're saying that 1 and 2 is already there. And all I want to say here, I want to calculate is the change in potential of the system when I bring the third one here. And that's why we can actually use this equation to calculate that, because those two were already there. Okay, so we are only looking at the change in potential energy of the Q3 when it comes from infinity to that point P. All right. So there is then that equation that we already looked at, where VB minus VA equals negative of integral of E dot ds. Okay, so again, this is the important equation for us. So if we go back to this equation, one thing we can see here is this. There is a way to go around and kind of reverse engineer this equation. See, what we're doing here is this, calculating delta V from the line integral of E dot ds. Okay. But if we kind of go other way around, we can actually see that we can find, expression where if I take the basic derivative of both sides, right? So then I can look at it in terms of dV, okay? So potential difference dV between 2 points at a distance ds apart, and this becomes negative E dot ds. Okay, so dV equals negative E dot ds. And if I divide both sides by ds, okay, then what I end up with is this. Electric field is equals to, move the negative to the other side, becomes then dV over ds. That means I can look at it in terms of potential, derivative of the potential with respect to the position to get then the electric field. That means if you have the, let's say point A, point B, and you have a potential that changes as a function of position, and we know that it does, right? We can use that, which is the rate at which it changes as a function of position. So that rate then can give us electric field. So the negative of the derivative of the V with respect to S is the electric field. All right. So now this is, let's say, would have been if it's one-dimensional, but obviously this could be two-dimensional. Point B could be here. So we can actually move like this. Or it can be three-dimensional, where this is somewhere like that, right? That means we can look at it in terms of that electric field in that region, right, to be either one-dimensional or two-dimensional or three-dimensional. So that's why, in a way, what we have is that this E dot ds can be Ex dx. So that in that case, this is just in terms of horizontal, then dV equals negative Ex dx, then divide both sides by dx, and we get then only the x component of the electric field by looking at how the potential changes as a function of horizontal position. Okay, so Ex equals negative dV over dx. For example, if you have a potential that is, let's say, 3x squared, right? For example, then take the derivative of this one. So the electric field will be equal to negative dV dx. So this will be negative 6x. So then negative 6x is then the electric field. Okay, so that means this gives you the magnitude of the electric field along that, some 2 points on a horizontal axis. Okay, so then this will be in terms of taking the derivative of that potential as a function of x and finding the electric field, which tells you that electric field also non-uniform, it actually changes with position as 6x. All right, so now if the charge distribution creating the field has spherical symmetry, for example, as I mentioned, right? It could be one-dimensional, two-dimensional, three-dimensional. The electric field is radial, and then ER is equals to then negative dV dr. Okay, so in general, the electric potential is a function of all three dimensions, and given that potential can change as a function of x, y, and z, you can find x, y, and z components of the electric field by taking the derivative of the function, specifically as a function, find the x, you take the derivative with respect to x. To find the y component of the electric field, you take the derivative with respect to y only. If you want the z component, you take the derivative of the z only. Okay, so these are known as a partial derivatives, okay, which is basically same as the regular derivative, but what you do here, you keep everything constant except the quantity that you want. Okay, so let's say you take in derivative with respect to. So let me show you, like, let's say a quick example. All right, so let's say we have v as a function of x, y, and z that is equals to, for example, 3xy squared plus, let's say 4zy cube x, something like that. So then what we can do here is this. We can say that, all right, so we're finding then the electric field, but instead we're going to look at in terms of electric field in the x direction, electric field in the y direction, electric field in the z direction, basically finding components first. Electric field in the x direction is equal to the negative of, then this is partial derivative of v with respect to x. What it means that if I'm taking the derivative of this function, everything is a constant but x. That means y is a constant, z is a constant. So then if I'm doing this, then it becomes negative. So then let's take this derivative of this one as a function of x. 3xy cubed, y squared, just becomes 3y squared, because I'm only treating, x as something that I'm taking derivative with respect to. Everything else is a constant. Then plus, then 4zy cubed x, then gives me 4zy cubed. And then finally put the negative, so it becomes negative 3y squared minus 4zy cubed. Right. So let's look at in terms of the y component of the electric field. Well, this is then partial derivative of the v with respect to y. That means negative, and then I take the derivative of this function again, but this time everything is constant but y. So it becomes then 3xy squared becomes then 6xy, then plus 4zy cubed x becomes then 12zy squared x. Okay, and then this is negative 6xy minus 12zy squared x. Finally, derivative of z, negative partial derivative of v with respect to z is equals to, again, take the derivative of the function where everything is constant but z. So first term has no z, so it's 0, because that means that's all constant, nothing, no z over there. Then, well, there's a negative there, right? And then plus 4zy cubed x becomes 4y cubed x. That means the z component is negative 4y cubed x. That means this is the x component, this is the y component, and then this is the z component of the electric field. Now, how do I find the direct magnitude of the electric field? Well, magnitude will be square root of ex squared plus ey squared plus then ez squared, right? Plug in everything and then just calculate the magnitude. All right, that, pretty straightforward, even though it's a partial derivatives, right? But it's just a regular derivative where you are taking the derivative with respect to just one, variable. All right, so let's go back here. So the next we're going to talk about equipotential surfaces. So we already kind of mentioned that, right? If you have a electric field, so like let's say, or a source charge, because of that electric field, then let's say the source charge creates an electric field around it that moving, let's say, radially outward, but also we can find positions where the potential is exactly the same. We call them equipotential surfaces. And you can see, right, those circles around, for this one, those are equipotential surfaces. And one important thing about equipotential surfaces and electric field lines is that they're always perpendicular to one another. That means we cannot really see electric field lines, but we can measure the equipotentials. And once I draw those blue lines, then I can use them to technically draw the electric field. We have a lab on that, because electric field will always move such that it's perpendicular to the equipotential, and it always goes from, higher to lower. That means, let's say this point 1 and this point 2. I know that if I measure potential at point 1, it's higher than potential at point 2. I know in which direction the electric field is moving from high to low. It's always like that. And here's another one, right? So you can see, right, electric field is uniform to the right. Then you can look at in terms of equipotential surfaces. Again, the key here is they're perpendicular, right? Electric field and equipotentials are all perpendicular. Even for electric dipole, again, you have exactly same thing where electric field is perpendicular to the equipotentials. And this is something we're going to also explore in the lab. We're going to be able to see that, in terms of something like that or parallel plates, how we can find the electric field from, the equipotentials. All right. So here's one more example. And this one basically kind of demonstrates what we just, allows us to calculate what we just, learned in terms of those equations. So the idea here is that if I have those two charges, Q1 and Q2, for example, and if I want to find electric field at that point X, we learned how to do that in previous chapters. We can use basically the electric field equation for Q and Q1, like let's say Q1 and Q2, find the electric field X component, Y component, and all of those things at that point X, and then add them as vectors and all that thing. But there's another way doing that, because I know one thing, right? I can always find electric field if I have the potential. And it's much easier to find the potential for a configuration like this. And that's what we're going to do. Two positive point charges, each have a charge of plus Q and are fixed on the y-axis at y equals plus A and y equals minus A. Find the electric potential at any point on the x-axis. So let's choose this point X. So we're going to say that I'm going to find the position at the potential at point X. Well, that means since both of them are distance A from the origin, that means this R is the same for both of them, and their charges are the same as well. So potential 1 plus potential 2, which is my net potential, will be KQ1 over R1 plus KQ2 over R2. But since Q1 equals Q2, R1 equals R2, so this is basically 2KQ over R. Okay, which is then 2 times 9 times 10 to the 9, then, well, we're not given the value. So let's say we have that, 2KQ over R. Okay, well, now let's do this. Okay, so what is R? I can represent R in terms of then, so let's say 2KQ over square root of x squared plus a squared. So that's one thing I can do. But this is my net potential at that point X. Okay, so part B says then use your result with part A to find the electric field at any point on the x-axis. You can see, right? In a way, this X basically can be anything. It can be 1 meter, 10 meters, and thing like that, right? I'm going to get the same expression. Now, how do I find the electric field? Well, I know that electric field is equals to negative derivative of the potential with respect to R. But this is only in terms of the horizontal axis, right? Anywhere on the x-axis. So then technically it's negative, partial derivative of the, with respect to x. I can put I hat as a, unit vector indicating that it's horizontal. Okay. That means I'm doing then the derivative of this, right? 2KQ over square root of x squared plus a squared. Okay. Now, if I'm, and this is the x component, right? So if I'm doing then the derivative of this one, I can see that, so technically the 2KQ is a constant, so it can come out. So then I'm doing the derivative of pretty much this, right? X squared plus a squared negative 1/2. All right, so if I do that, then what I end up with this 2KQ of negative 1 over x squared plus a squared 3/2. You can take the derivative of that one, and this is what you get. So then negatives cancel out. So then the electric field is equal to then 2. Oh, actually, like let's say then I have to do the derivative of the argument, which then gives me 2x. X squared, then the derivative of that becomes 2x. I don't know, so I can ignore that one. So it becomes 2x because I take the derivative of this first, which gives me negative 1 over x squared plus a squared 3/2. And then I do the derivative of the argument of the x squared, then that gives me 2x. So then becomes, 2 um, Well, I'm forgetting there's also 1/2 factor over there because this 1/2 also goes there. All right, anyway, so 2, this 1/2 cancels with that. K Q X over X squared plus A squared 3/2 I hat. And that's going to be basically the electric field at that position. Again, so what we did here, we took the derivative of the X squared minus A squared negative 1/2, and use that, right? Take the derivative of that and use that to find the electric field, because what we did here is we took the derivative of the potential as a function of X.